Hello there, and welcome to the Sleep with Science channel. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps the channel to reach more curious minds like yours. Now let's begin. Somewhere beneath the quiet hills near Geneva, far below the fields and the farmhouses and the sleeping villages of the Franco-Swiss border, there is a ring of steel and glass 27 kilometers around, cooled colder than the empty space between galaxies. And in that ring, in complete darkness, something extraordinary has been happening. Protons, smaller than anything you could ever picture, are being hurled toward one another at nearly the speed of light, colliding billions of times each second, shattering into fragments of pure energy. Scientists call this place CERN. And recently, in the quiet aftermath of one of the most delicate experiments ever performed there, a question surfaced. A question so vast, so strange, that even the researchers themselves have described it in hushed, careful language. Not a question about what the universe is made of. Not a question about where it came from. But a question about how it might end. Not with fire. Not with a bang. But with something far quieter, far stranger, something called vacuum decay. Somewhere in the data, in the invisible dance of particles too small to see, there may be a hint, a whisper, of an instability sitting at the very heart of everything that exists. An instability that, if it is real, means the universe you are lying in right now, this very moment, might not be as permanent as it feels. Stay with me here, because this is not a story of fear. It is a story of wonder, of scale, of the strange, beautiful fragility that may be woven into the fabric of existence itself. And to understand it, we have to travel down past the surface of the earth, down into that dark tunnel, down into the smallest measurable pieces of reality. Let your body soften now. Let your shoulders sink into whatever is holding you. There is nothing you need to do right now except listen and breathe and drift gently alongside this journey. Picture that tunnel beneath the Swiss countryside, a perfect circle of magnets and mirrors and wire, kept colder than the coldest reaches of interstellar space, colder than the dark side of Pluto, colder almost than the universe itself has any right to be. This is the Large Hadron Collider. For years, scientists have used it to smash protons together, recreating, for the briefest fraction of an instant, conditions that have not existed since the first trillionth of a second after the Big Bang. In 2012, inside this very tunnel, researchers confirmed the existence of a particle theorists had predicted decades earlier. The Higgs boson, a quiet, invisible field that fills the entirety of space, giving mass to nearly everything that has ever existed. Without it, there would be no stars, no planets, no gentle weight of a blanket settling over you as you drift toward sleep. But the Higgs field carries with it a secret, a number, a precise measured value that determines whether the universe we live in is stable or whether it is merely sitting, quietly, in a shallow valley, when a deeper, darker valley waits somewhere beyond it. Physicists have a name for this deeper valley. They call it the true vacuum. And our universe, the one holding you, this room, this soft darkness around you, may be resting instead in what they call a false vacuum. A place that feels permanent. A place that has lasted for nearly 14 billion years without incident. But permanence, in physics, is not the same as certainty. Let that settle over you gently, like a slow tide moving in across a dark and silent shore, because in the newest measurements taken at CERN, in the refined mass of that quiet Higgs particle, something in the numbers has shifted, ever so slightly, toward a valley we do not yet fully understand. There is no need to hold this tightly. Let it simply drift past you the way a distant comet drifts past a sleeping planet, slow and indifferent to the hour. Because if this deeper valley exists somewhere out there, physicists believe it would not announce itself with sirens or warnings. There would be no countdown, no trembling of the ground. Somewhere, at some quiet, unknowable point, a single, impossibly small bubble of true vacuum might slowly begin. And it would expand outward in every direction at the speed of light itself, rewriting the laws of physics as it moved, unseen by anyone until the moment it arrived. You would never see it coming. There would be nothing to feel, nothing to fear, only the universe gently becoming something else entirely. This is the strange, quiet possibility that CERN's latest measurements have nudged back into the light, a possibility resting somewhere far beyond tomorrow, beyond every star you have ever wished upon. And to understand how far away that possibility lives, we need to travel back to the moment this idea was born, back to a small, unassuming laboratory where a group of tired, brilliant physicists began to suspect that the ground beneath all of existence might not be as solid as it seemed. This was not a story that began at CERN. It began decades earlier, in the 1970s and 80s, in the quiet offices of theoretical physicists who spent their days not looking through telescopes, but scribbling equations on chalkboards, searching for cracks in the mathematics of reality itself. There was a man named Sidney Coleman, a physicist at Harvard, known for a mind so precise, so patient, that colleagues would gather simply to watch him think out loud. And somewhere in that quiet, unhurried work, Coleman began to ask a question that most people never think to ask. What if empty space itself is not truly empty? What if the vacuum, the nothingness between the stars, the silence surrounding this very room around you now, is not a fixed and final thing, but something that could, in theory, change? Let that thought settle slowly, like snow falling without a sound. Because in physics, a vacuum is not simply the absence of matter. It is a state, a configuration, a kind of resting point for the invisible fields that stretch across the entirety of the cosmos. And resting points in nature are not all created equal. Think of a marble resting inside a shallow bowl, perched near the top of a gentle slope, appearing calm, appearing settled, while just beyond the rim of that bowl, hidden from view, there lies a much deeper basin, one the marble has never discovered, because nothing has ever nudged it hard enough to fall. This is the quiet, patient image physicists still use today. Our universe, they suggest, may be that marble. Comfortable. Stable enough to last for billions upon billions of years. Stable enough to build galaxies, and stars, and quiet oceans, and the slow, steady rhythm of your own breathing right now. But perhaps not resting in the deepest, truest valley the universe could occupy. In 1980, Coleman worked alongside a physicist named Frank DeLucia, and together they published a paper that would quietly echo through physics for the next half-century. In it, they described, with careful mathematical precision, exactly how a false vacuum might someday collapse into a true one. Not through any external disaster, not through a collision, or an explosion, or anything reaching in from outside, but through something called quantum tunneling, a strange and gentle process, where, given enough time, a tiny bubble of true vacuum could simply appear out of nothing at all, born from the same quiet uncertainty that lets particles blink in and out of existence in the emptiest corners of space. And once that bubble formed, it would not stay small. It would grow, expanding outward at the speed of light in every direction at once, converting the false vacuum into the true one as it moved, silent, invisible, and utterly without mercy for anything in its path. For decades, this remained a beautiful, unsettling piece of theory. Elegant on paper, but resting on numbers no one could measure precisely enough to know whether it applied to our universe at all. Because whether we are living inside a stable vacuum or a false one depends entirely on two numbers. Two masses. The mass of the Higgs boson, that quiet field which gives weight to nearly everything around you, and the mass of something called the top quark, the heaviest of all known fundamental particles, a fleeting, unstable thing that exists for less than a trillionth of a second before decaying away into lighter fragments. These two numbers, when placed together on a graph and measured against each other with almost impossible precision, decide the fate of everything. If the top quark had been just slightly lighter, or the Higgs just slightly heavier, our universe would sit comfortably, safely, in the deepest valley available to it. Utterly and permanently stable. And if the numbers had leaned the other way, we would already know we were doomed, resting in a vacuum so unstable it could collapse at almost any moment. But the numbers, as they have been measured again and again over the past decade, do not fall clearly into either of those categories. They fall, instead, into a strange, narrow, uncomfortable middle ground. A place physicists have come to call, quite simply, the edge. Let your breathing slow as you sit with that word. The edge. Not catastrophe. Not safety. Something in between, something delicate, something that seems to require almost impossible fine-tuning to exist at all, as though the universe were balanced, deliberately or not, on the thinnest imaginable line between permanence and collapse. For years, this edge remained just barely on the safe side of the equation, close enough to unsettle theorists, but not close enough to demand alarm. And then, more recently, inside that same tunnel beneath the Swiss countryside, using detectors more sensitive than anything Coleman or DeLucia could have imagined in their lifetimes, scientists began refining those measurements once again, chasing the mass of the top quark and the Higgs boson down to fractions of a percent, hoping simply to confirm what had always seemed to be true. What they found instead, tucked quietly inside the newest data, gathered over months of patient, careful observation deep beneath those quiet Swiss hills, was something that made several quietly cautious, soft-spoken physicists in the room fall silent. Not from panic. Physicists rarely panic. Their training teaches them to sit with strange numbers the way a sailor sits with a shifting wind, alert, but composed. What silenced them instead was something quieter than fear. It was recognition. The refined measurement of the top quark, gathered from thousands upon thousands of collisions inside that dark, cold ring beneath the Earth, had nudged, ever so slightly, in a direction that made the shallow valley we call home seem just a little less secure than it had the year before. Not dramatically. Not suddenly. The shift was measured in fractions of a percent, in decimal places most of us will never think about in an entire lifetime. But in the strange arithmetic of vacuum stability, fractions of a percent are not small at all. They are the difference between a universe resting safely at the bottom of its valley for all of time, and a universe perched, quietly, uncomfortably, near the edge of a slope it may not fully understand. Let your breath settle here for a moment. In slowly, and out, even slower. Because before this thought carries you anywhere frightening, there is something essential you need to hold on to, something the physicists themselves would want you to know before anything else. Even in the most unsettling version of these calculations, even in the scenario where our universe is not perfectly stable but only metastable, resting in that shallow, false valley rather than the deep true one, the timescales involved are almost impossible for a human mind to hold. Not thousands of years. Not millions. Not even billions, though our universe has already existed for nearly 14 billion years without the slightest hint of trouble. The number physicists use, when they speak of how long a metastable vacuum might last before quantum tunneling ever produces a bubble of true vacuum, is a number so large it barely resembles a number at all. It looks more like a poem written in exponents. 10 raised to the power of over 100 years. A quantity so vast that if you tried to write every zero by hand, one every second, you would still be writing long after every star currently burning in the night sky above you had quietly gone dark on its own. So let that settle over you now, slow and heavy, like a blanket pulled gently up to your shoulders. Whatever this instability may be, whatever strange and delicate balance the universe seems to be resting upon, it is not a countdown clock ticking toward tomorrow, or next year, or even the next 100 generations of human beings who might one day look up at these same constellations. It is closer to a question about the nature of eternity itself, a question about whether forever, as we imagine it, is actually built into the architecture of the cosmos, or whether even forever has a quiet, distant boundary somewhere far beyond the reach of any calendar. This is the strange gift hidden inside frightening physics. The scale is so vast that fear simply cannot hold on to it. It slips away, the way a worry slips away in the final moments before sleep, replaced instead by something closer to wonder. And yet, the physicists at CERN did not stop simply because the numbers were reassuring on the timescale of human civilization. Because science, at its best, is not satisfied by reassurance. It is only satisfied by understanding. And so, in the months that followed those refined measurements, teams working across multiple experiments, some watching for the faint signatures of top quarks decaying into lighter particles, others recalibrating the exact mass of the Higgs boson itself, began comparing their results against each other with a kind of quiet, meticulous urgency. Because if the universe truly is metastable, if it is resting in that shallow valley rather than the deep one, that fact alone would not simply be an interesting footnote in a physics journal. It would reshape one of the oldest questions human beings have ever asked, standing beneath a sky full of stars and wondering how the story of everything eventually comes to a close. For centuries, that question belonged to poets and prophets and philosophers, each offering their own quiet vision of endings, fire, ice, silence, rebirth. But for the first time in human history, that question had quietly slipped into the hands of experimentalists working with magnets and detectors and unimaginably precise instruments, capable of measuring a particle's mass down to a fraction most of us could never picture. The universe, it seemed, might finally be willing to answer, in its own patient mathematical language, the very question it had spent billions of years keeping silent, the question of whether the darkness surrounding you right now, this soft and ordinary night, is a permanent fixture of existence, or simply the longest pause the cosmos has ever managed to take. Let yourself rest inside that pause a little longer, because there is no need to rush toward an answer tonight. The scientists spent decades gathering courage to ask this properly, trusting numbers that whisper. And to understand what their answer might mean, we need to travel even deeper still, past the Higgs field, past the top quark, down into the strange, invisible architecture of empty space itself, past even the smallest particles ever measured, into the quantum foam that physicists believe underlies everything you can see and everything you cannot. Imagine, for a moment, zooming in on the empty space in front of you. Not the room around you, not the air, but the space itself, the nothingness between one point and another. Zoom in past the smallest speck of dust, past the smallest atom, past even the tiny particles that make up that atom, the quarks and electrons that seem, at our scale, like the final answer to what things are made of. Keep going, down past distances so small that ordinary numbers stop being useful, down to what physicists call the Planck length, a scale roughly 100 billion times smaller than a single proton. At that depth, something strange begins to happen. Space itself stops looking smooth. It stops looking like the calm, silent backdrop you imagine when you gaze up at a clear night sky. Instead, it begins to churn, to froth, to flicker in and out of existence in ways that defy nearly everything your intuition tells you about how the world should behave. Physicists call this the quantum foam. And it is not simply a metaphor, not simply a comforting image meant to help the mind grasp something too strange to picture directly. It describes something physicists believe to be genuinely, mathematically true. At the smallest possible scales, empty space is never truly still. Pairs of particles, a particle and its opposite, its antimatter twin, are constantly winking into being out of pure nothing, existing for an instant so brief it cannot be measured by any clock ever built, and then annihilating each other, vanishing back into the vacuum from which they came. This happens everywhere. It is happening right now, in the space between your fingertips, in the space filling this room, in the space stretching between every star you have ever looked up and wondered about. Trillions of these tiny, fleeting events, flickering in and out like the faintest static on the oldest television you can remember, a constant, silent hum of near-nothingness that never quite settles into true nothingness at all. Let this thought move through you slowly, the way warmth moves through a body sinking into a soft bed. Empty space, the very thing we imagine as the absence of everything, turns out to be one of the most restless, most active places in the entire universe, simply too small and too fast for anything we have ever built to observe directly. And it is inside this restless, flickering foam that the question of vacuum decay truly lives. Because if our universe is indeed resting in a false vacuum, a shallow valley rather than the deepest one available, then somewhere within that endless flickering of particles winking in and out of existence, there exists a vanishingly small, but not impossible, chance that one of those fleeting fluctuations could, by pure chance, tunnel its way into the deeper, truer valley. Not through any dramatic event. Not through any collision powerful enough to notice. Simply through the ordinary, restless nature of empty space itself, doing what it has always done, quietly, patiently, for longer than any star has burned. This is part of why physicists find the concept so hauntingly beautiful rather than simply frightening. The ending it describes, if it is real at all, would not come from some external threat reaching in from outside the universe. It would not come from a wandering asteroid, or a dying sun, or any of the more familiar endings human beings have imagined for millennia. It would come from within. From the deepest, quietest interior of existence itself, from the same subtle quantum uncertainty that gives rise to starlight, to chemistry, to the very atoms holding your body together as you lie here now. The universe, in this strange telling, would not be destroyed by anything foreign to it. It would simply, one day, finish becoming more fully itself, settling at last into the deepest resting place available to it, the way a stone eventually settles at the bottom of a lake after enough time has passed for every ripple to fade. And this is precisely why the measurements taken at CERN matter so much to this particular story. Because whether that deeper valley exists at all, and whether our universe is truly positioned close enough to the edge for such a transition to ever become possible, depends entirely on the same two numbers we have already spoken of, quietly repeating themselves at every scale of the story like a familiar and steady heartbeat. The mass of the Higgs boson. The mass of the top quark. Two invisible measurements, hidden inside collisions too fast and too small for any human eye to witness directly, and yet powerful enough to determine whether the quantum foam surrounding you at this very moment is dancing atop a stable foundation, or resting, quietly, uncertainly, above something far deeper still. Let your mind rest on that image a little longer, the foam, the flicker, the endless soft churning beneath everything solid you have ever touched, all of it tracing back, in the end, to those same two patient numbers, waiting inside a mountain of collision data for someone careful enough and quiet enough to finally read what they have been trying to say, something physicists have quietly spent the better part of a century trying to hear clearly enough to answer a question too large, perhaps, for any single mind to hold alone. Not whether the universe will end, for endings, in one form or another, seem now unavoidable in nearly every model physicists have built, but when and how. Whether gently, like a tide receding from a shoreline no one remembers being full, or violently, in a single unannounced instant, spreading outward at the speed of light itself, erasing everything it touches without so much as a flicker of warning beforehand. Picture, if you can, a landscape, not of hills and valleys carved from stone, but of energy itself, curving and dipping across a mathematical terrain that no telescope could ever photograph, and no hand could ever touch. Physicists call it a potential, a kind of invisible topography that describes, at every possible value of the Higgs field, how much energy the universe would hold if it settled there. And our universe, this one, the one holding you now, beneath whatever blankets or shadows or quiet hours surround you, appears to be resting in a small dip along that landscape. A shallow place. A comfortable place, for now. But not, if the numbers are read correctly, the deepest place available. Somewhere further along that same curve, hidden past a ridge of energy so immense it might as well be called a mountain, there may lie another valley. Lower, deeper, more stable, in the strict thermodynamic sense that physics reserves for the word. And the unsettling truth, the one that has kept theorists awake, quietly, carefully, the way this story now asks you to rest instead, is that a universe sitting in a shallow valley beside a deeper one is not, technically speaking, in its most stable form. It is what is called metastable. Stable enough to last. Stable enough to raise stars and oceans and every quiet breath you have ever taken. But not, perhaps, stable forever. This is not science fiction. This is the language of quantum field theory, written out in equations that have been checked and rechecked against real collisions inside real machines buried beneath the hills near Geneva. The Large Hadron Collider, that vast underground ring where protons are accelerated to within a hair's breadth of light speed before being allowed, gently, deliberately, to collide. And in the debris of those collisions, in the brief and blinding aftermath, particles appear that exist for less time than it takes light to cross a single atom. Among them, if the energy is tuned just right, a Higgs boson. And in other collisions, a top quark, the heaviest of all known elementary particles, so massive that it decays before it ever has the chance to form anything resembling matter at all. Each measurement refines the picture. The Higgs mass, drifting somewhere near 125.25 billion electron volts. The top quark mass, closer to 172.5. Numbers that mean nothing to most of the universe, and everything to the question of its fate. Because when physicists plot these two values against each other, on a graph built from decades of theoretical work, they find our universe sitting not comfortably in the middle of the stable region, and not safely inside the region where collapse is impossible, but balanced, almost improbably, along the narrow border between stability and its opposite. A border so narrow that earlier generations of physicists, working with cruder instruments and wider margins of error, could not have known how close to that edge reality truly sits. It is, some have said, as though the universe were built along a knife's edge, and simply happened to survive the fall onto one side of it. Whether that is coincidence, or consequence, or the quiet residue of some deeper symmetry not yet understood, remains one of the open wounds of modern physics. But the calculation itself is not mysticism. It follows directly from the Standard Model, extended out to energies far beyond what any collider could ever directly probe, all the way up toward the Planck scale, where gravity and quantum mechanics are believed to finally meet, and where our current equations, admittedly, begin to lose their footing. And so the story becomes one of extrapolation, of taking numbers measured with exquisite care in a tunnel 27 kilometers in circumference, and extending them, mathematically, across 16 orders of magnitude in energy, out to a scale so far beyond anything nature offers us directly that words like far begin to lose their meaning. It is a leap of enormous trust in the consistency of physical law. And yet, so far, every test performed at every accessible energy has agreed with what the equations predicted, which is, in its own quiet way, a kind of miracle, or at least the closest thing physics allows itself to call one. If the vacuum is indeed metastable, then somewhere, at some point in an almost incomprehensibly distant future, a tiny bubble of true vacuum could, in principle, come into being, not through any human action, not through any collider, but through the ordinary, ceaseless quantum fluctuation of empty space itself, patiently rolling dice across billions upon billions of years, waiting for the rarest possible outcome to finally occur. A single point, smaller than a proton, smaller than anything the word small was ever meant to describe, where the field finally tunnels through that mountain of energy rather than waiting to climb over it. Quantum mechanics allows this, insists upon it, in fact. Given enough time, and enough space, and enough attempts, even the most forbidden transitions become, eventually, permitted. This is the same strange permission that lets particles pass through barriers no classical object could ever cross, the same quiet rule-breaking that powers the radioactive decay of atoms, scaled upward now to the very fabric that atoms themselves are woven from. Should such a bubble form, it would not remain small for long. Inside it, the Higgs field would settle into that deeper valley, that lower, truer minimum, and in doing so would release energy, not as heat in any familiar sense, but as a fundamental rewriting of the rules governing mass and charge and the strength of every force holding matter together. The bubble wall would begin to expand. And because there is, within it, no longer any barrier holding it back, no ridge left to climb, it would accelerate outward at a fraction of the speed of light approaching unity itself. Some calculations suggest it would reach nearly the full speed of light within an astonishingly short distance, the wall of new physics chasing the wall of light so closely that nothing inside the old vacuum could ever detect its approach. Not a telescope. Not a warning system. Not even the frantic firing of a single neuron trying, uselessly, to register alarm. This is perhaps the strangest mercy hidden inside an otherwise unsettling idea. If the true vacuum bubble were to form somewhere in the observable universe and begin its expansion, there would be no observation of it beforehand. No dimming of stars. No trembling in the fabric of space-time detectable by our finest instruments. Light itself, the very messenger that carries all warning, all knowledge, all awareness across the universe, travels at exactly the speed the bubble wall approaches, which means the wall and the news of the wall would arrive together, indistinguishable, in the same silent instant. One moment, the ordinary hum of existence. The next, nothing recognizable as existence at all. Not death, in the way the word is normally used. Something closer to a rewriting. A universe still present, still full, but built from entirely different rules than the ones your body, right now, quietly depends on to keep beating, breathing, existing. It is worth pausing here, gently, to hold two truths side by side without letting either one collapse into panic. The first is that this scenario, cosmologists estimate, would require timescales so vast that the current age of the universe, nearly 14 billion years, amounts to little more than a single heartbeat by comparison. Some calculations place the expected lifetime of a metastable vacuum, under the values measured so far, at numbers followed by so many zeros that writing them out serves no purpose beyond illustrating just how comfortably unlikely tomorrow remains. The second truth is that these numbers depend entirely on the precision of measurements still being refined, quietly, patiently, inside detectors named Atlas and CMS, buried in the same tunnel where protons complete 11,000 revolutions every single second, colliding, scattering, decaying, leaving behind traces that take years of careful analysis to fully understand. And so the physicists return, again and again, to those same two numbers. Refining the mass of the Higgs boson by fractions of a percent. Refining the mass of the top quark with the same devoted patience. Not because they expect to find comfort in doing so, and not because they expect to find catastrophe either, but because uncertainty itself, left unexamined, is its own kind of quiet unease. Better, they seem to believe, to know precisely where the universe stands, even balanced on the narrowest of borders, than to guess. There is something almost meditative in this pursuit, if you allow yourself to sit with it a while longer. An enormous machine, built by tens of thousands of hands across dozens of nations, constructed for the sole purpose of asking the universe, again and again, to reveal a little more of what it is quietly made from. Protons collide. Detectors listen. Data accumulates, terabyte upon terabyte, year upon year, and slowly, so slowly, out of that seemingly chaotic storm of collisions, two numbers emerge with ever-tightening precision, describing not just particles, but the very shape of the vacuum in which every star, every atom, every breath you have ever taken has been quietly, unknowingly resting all along. Let that thought settle now, without urgency, without fear, the way sand settles at the bottom of still water. The universe you inhabit may be stable for all practical purposes, for timescales so long that no human concept of waiting could ever meaningfully apply to them. And yet the mere possibility, written faithfully into the mathematics, invites a different kind of wonder altogether, the recognition that existence itself may be less like a solid floor beneath your feet, and more like a great dark sea, calm on its surface, and yet resting above depths whose true nature remains, even now, only partially understood. A sea that has, so far, only ever shown you its stillness, never its floor. Let us drift for a while, away from the language of collapse, and toward the instruments themselves, because it is worth understanding, slowly and without hurry, how such impossibly small numbers come to be known at all. Beneath the border of France and Switzerland, in a tunnel first carved for a different experiment entirely, protons are guided by superconducting magnets cooled to temperatures colder than the empty space between galaxies. Colder, in fact, than almost anywhere else in the observable universe, since even the void between stars retains the faint afterglow of the Big Bang, a whisper of warmth measured at 2.7 degrees above absolute zero. The magnets guiding those protons are cooled lower still, so that electrical current can flow through them without resistance, without loss, bending beams of protons around a ring 27 kilometers in circumference with a precision measured in fractions of a millimeter. Two beams, traveling in opposite directions, brought together at 4 points around that ring, where detectors the size of cathedrals wait in the darkness for something to happen. And when the beams cross, most protons pass through each other entirely undisturbed, two clouds of matter occupying the same space and time without so much as touching, because protons, despite their solidity in the human imagination, are mostly empty space themselves, quarks and gluons separated by distances that dwarf their own size the way a handful of fireflies might dwarf the darkness of an entire night sky. But occasionally, rarely, perhaps once in many millions of crossings, two protons meet closely enough for their inner constituents to actually collide. And in that collision, for a fraction of a second, energy is concentrated into a space smaller than the proton itself, hot enough and dense enough to briefly recreate conditions unseen since the earliest moments after the Big Bang. It is in this fleeting furnace that new particles can be born. Not from nothing, but from the pure conversion of energy into mass, following the same equation a young patent clerk once wrote on paper more than a century ago, that quiet equivalence between energy and matter that still governs, without exception, every collision inside that tunnel today. Most of these newborn particles are unstable, existing for less time than light takes to cross a single hydrogen atom before decaying into other, lighter particles, which decay again and again, in a cascading pattern that detectors must reconstruct backward, like archaeologists piecing together a vanished civilization from nothing more than scattered fragments and the faint impressions left in surrounding stone. A Higgs boson, when it forms, does not sit still long enough to be observed directly. It exists and then it is gone, leaving behind only its decay products, only clues, perhaps two photons, appearing at very particular angles and energies. Perhaps four leptons, tracing delicate curved paths through the magnetic field of the detector, paths that reveal, upon careful measurement, both their charge and their momentum. From thousands upon thousands of these events, gathered patiently over years, layered together like sediment settling slowly at the bottom of that dark and quiet sea, a pattern begins to emerge. A small excess of events clustering around a particular energy. A bump, physicists call it, rising gently above the smooth background of ordinary particle interactions, and it was exactly such a bump, observed independently by two separate detectors in the summer of 2012, that first confirmed the Higgs boson's existence and gave physicists their first real measurement of its mass. The top quark tells a similarly patient story, though it was found earlier, in 1995, at a different collider altogether, before the Large Hadron Collider had even been built. And it remains, even now, extraordinarily difficult to pin down with precision, because unlike lighter particles, the top quark decays before it has time to form any of the composite particles that quarks usually build, meaning physicists must reconstruct its mass indirectly, through careful and painstaking analysis of everything it leaves behind. Each new run of the collider adds a little more precision. Each careful reanalysis of old data shaves the uncertainty down by another sliver, moving the decimal point one place further, tightening the range within which the true value must lie. It is slow work, unglamorous, in the way that most real discoveries tend to be, far removed from the popular image of a sudden eureka moment arriving in a flash of insight. There is no single instant in which the fate of the universe becomes known. There is only this: thousands of researchers, spread across dozens of countries, quietly refining numbers that grow, year by year, closer to whatever truth they are approaching, the way a sculptor might work not by adding material but by patiently removing everything that is not. Picture from one category into another entirely, from a universe destined, in some far and comfortable future, to persist in gentle stability, into one instead quietly marked, from its very first instant, as temporary. Not fragile in any way that need trouble your evening, not fragile in any way that touches tomorrow, or next year, or the next 10,000 generations that might follow after you, but fragile across the kind of timescale that makes 10,000 generations look like the space between one breath and the next. It may help here to leave the language of catastrophe behind for a while, and rest instead in the company of numbers themselves, because numbers, examined slowly enough, have their own kind of quiet beauty, independent of whatever they ultimately predict. Consider the electron volt, that strange unit physicists reach for when ordinary joules become too clumsy, too large, to describe anything happening at the scale of a single particle. 1 electron volt is the energy gained by a single electron accelerated through a single volt of electric potential. A minuscule thing. And yet the Higgs boson carries a mass energy of 125 billion of them. The top quark, heavier still, carries nearly 173 billion. To hold these numbers is to hold, in some abstracted and mathematical way, two of the heaviest fundamental particles known to exist, both of them invisible, both of them fleeting, both of them essential to the architecture of everything solid. It is worth remembering, too, that mass itself, at this level, is not quite the simple, intuitive property it seems to be in ordinary life. The Higgs field does not merely create the top quark's mass out of nothing. Rather, it is the strength of the top quark's coupling to that field, its interaction with the quiet, invisible presence that fills all of space, which determines how heavy it becomes. The top quark couples to the Higgs field more strongly than any other known particle, almost as strongly as the mathematics allows before certain symmetries would break down entirely. This is not coincidence. Many physicists suspect this unusually strong coupling is precisely why the top quark's mass plays such an outsized role in determining the shape of the vacuum landscape, why its value, more than almost any other number in physics, tips the delicate balance between stability and its opposite. There is a kind of quiet symmetry, too, in the way these two particles seem bound together by fate, though they were discovered nearly 2 decades apart, through entirely different experiments, in entirely different corners of the world. The top quark, found first at Fermilab outside Chicago in the mid-1990s, in a collider now retired, its magnets cooled and quieted, its tunnels left to a kind of scientific retirement after decades of service. The Higgs boson, found later at CERN, in a machine built in part because of what the top quark's mass had already begun to suggest about where the Higgs itself might be hiding. Each measurement guided the search for the other. Each number quietly informed the next question. It is, in its own way, a story of one generation's discovery becoming the compass for the next. And now, in this present moment, in laboratories filled with a hush broken only by the low hum of cooling systems and computer servers processing petabytes of information, physicists continue refining both numbers still further, not toward some final headline-grabbing announcement, but toward smaller and smaller uncertainties, shaving decimal places the way a jeweler might polish a stone, patiently, invisibly, one imperceptible pass at a time. The most recent combined analyses place the top quark's mass with an uncertainty of less than 0.5%. The Higgs boson's mass is known with even greater precision still. And with every fraction of a percent gained, the picture of the vacuum shape grows a little sharper, a little more resolved. Like an image slowly developing in a darkroom, the outlines of something vast and quiet emerging gradually from what had once been undifferentiated gray. It is tempting, lying here in the stillness of your own evening, to imagine this process as something urgent, something racing toward an answer. But it is not that at all. It unfolds instead with the unhurried patience of geological time, compressed, strangely, into the working lives of a few thousand scientists scattered across the world, each one contributing some small fragment to a picture none of them will ever see completed within a single lifetime. Data is collected. Data is checked. Data is checked again, by different teams, using different methods, cross-referencing results the way two witnesses might quietly compare their memory of the same distant event, searching for where their accounts converge and where they diverge. And in that small space of divergence, that narrow margin where one measurement leans a fraction one way and another a fraction the other, lies the honest uncertainty of the universe itself, admitted rather than hidden, carried forward rather than smoothed away. This is not how certainty is often imagined. We tend to picture discovery as a door swinging open, a single bright moment when the unknown becomes known. But the story of the Higgs field, and the story of the vacuum it fills, has never worked that way. It has been built instead from thousands of quiet agreements, each one small, each one provisional, stacked patiently atop the last like stones laid without mortar, trusting only their own careful balance. A mass measured here. A decay rate measured there. A coupling constant, faint and difficult, coaxed out of billions of collisions that mostly show nothing at all, mostly show the ordinary, mostly confirm what was already suspected. Because that, too, is a kind of progress, the unglamorous kind, the kind that rarely makes headlines but without which no headline would ever be trustworthy. Consider, for a moment, what is actually being asked of these detectors. Two beams of protons, moving in opposite directions at nearly the speed of light, are brought together inside a ring 17 miles in circumference, buried beneath the Swiss and French countryside, beneath vineyards and farmland where, above ground, life continues in its usual unhurried way, cows grazing, church bells marking the hour, none of it aware of what is happening in the darkness below. When those protons collide, they do not simply break apart. They convert, briefly, into pure energy, and from that energy, in accordance with a century-old equation that still startles with its simplicity, new particles condense into being, flickering into existence and out of it again in less time than light takes to cross a single atom. Among the debris of these collisions, once in many billions, something resembling a Higgs boson appears. It does not linger. It cannot be seen directly. What the detectors register instead is its aftermath, the specific, telltale pattern of lighter particles into which it decays, a signature written in tracks of ionization and calorimeter energy, a kind of fingerprint left behind by something that was never meant to be observed by beings built from atoms so much larger, so much slower, so much more enduring than itself. And from millions of these fingerprints, gathered and sorted and statistically distilled, a number emerges. A mass. Roughly 125 billion electron volts, if you want the figure, though the figure itself matters less here than what it represents. A single, fixed value that determines, in part, the shape of the vacuum every one of us has spent our entire lives standing inside without once perceiving it. Change that number even slightly, and the equations describing the field's potential energy shift with it. The landscape tilts, the false valley we appear to occupy deepens or shallows, the distant, lower valley that may or may not exist grows nearer or more remote. It is a strange kind of intimacy, To think that a number measured 17 miles beneath the Jura Mountains might quietly encode something about the ultimate fate of everything, including this room, including this breath, including the quiet particular fact of your own body resting here in the dark. There is a second number the physicists need, one measured with almost as much care, though it comes from a different kind of particle entirely. The top quark, the heaviest fundamental particle known, so unstable it decays before it can even form the kind of matter we recognize, existing for less than a trillionth of a second before it is gone. Its mass matters too, because it feeds into the same equations, tugging the vacuum's potential in its own direction, its own quiet vote in a calculation none of us will live to see fully resolved. And here is where the geological patience becomes almost unbearable in its slowness. The two numbers, Higgs mass and top quark mass, sit so close to the boundary between stability and instability that even now, after more than a decade of increasingly refined measurement, the answer teeters. Not because the mathematics is unclear, but because the values themselves, wrung from nature through extraordinary effort, still carry uncertainties too wide to say with total confidence which side of that boundary we occupy. So the work continues. Not urgently, not anxiously, but steadily, the way a river continues, the way erosion continues, the way anything continues that has decided, in its own unhurried fashion, that it will get there eventually. New runs of the collider gather more collisions. Detectors are upgraded, made more sensitive, taught to notice fainter signals buried deeper in the noise. Theorists refine their calculations, accounting for effects once considered too small to matter, closing gaps between prediction and observation that were, until recently, invisible even to the sharpest instruments. And somewhere in the offices and control rooms scattered across that vast underground ring, someone is right now looking at a spreadsheet, a plot, a column of numbers that mean nothing to anyone outside a small circle of specialists, and is nonetheless looking at a fragment of the same question you might ask yourself in a quiet moment before sleep. Not whether the universe will end, because in some form, it certainly will, but when, a question so vast it can only be approached by degrees, one decimal point at a time, one small refinement after another, each one a little closer to something that will never quite arrive as a single revelation, but rather as a slow tightening of possibilities, a narrowing of the range within which the truth must lie. Because that, in the end, is what all of this amounts to. Not an answer, but a diminishing space of uncertainty, shrinking year by year, run by run, the way a fog thins gradually over a valley without ever announcing the precise moment the mountains become visible. If you could hold in your mind the full landscape of the Higgs potential, that undulating surface physicists sketch on whiteboards and in papers, dropping down from some high, unstable plateau into the shallow valley where we apparently rest, you would see that the question of the universe's fate is really a question of curvature, of whether the valley we occupy is the lowest point in existence, or merely a resting place, a ledge partway down a much longer descent, separated from the true minimum by a barrier of energy no larger, in principle, than the space between one quiet thought and the next. This is the strange arithmetic of a metastable vacuum. It does not require some external force to disturb it. It does not need a comet, a collision, a cosmic catastrophe arriving from beyond the reach of any telescope. All it requires, if the numbers fall a certain way, is chance, a random fluctuation, occurring anywhere in the vast expanse of space, at any moment across the whole unfathomable duration of cosmic time, in which a small region of the field tunnels, quantum mechanically, through the barrier separating this valley from the deeper one beyond it. Physicists call this bubble nucleation, and the phrase itself carries a strange, domestic gentleness, as though it were describing something that happens in a glass of soda water rather than in the fundamental fabric of reality. A bubble. Small at first, immeasurably small, a single point where the field has, in effect, changed its mind about what kind of vacuum it wants to be. Inside that bubble, the laws would not merely bend. They would be rewritten. The masses of particles, which depend on how strongly they couple to the Higgs field, would shift to new values, because the field itself would settle into a different configuration, a different depth in its own potential. Electrons might weigh differently, or not exist at the same stable radius around atomic nuclei, or fail to bind at all. Protons might no longer hold together. Chemistry, in the sense that allows carbon to form long chains and hydrogen to bond into water, might simply cease to function, replaced by some other regime entirely, one with its own rules, its own peculiar order, but almost certainly none of them compatible with anything resembling a body, a breath, a memory, a name. And then, having formed, that bubble would not stay small. Because the interior would represent a lower energy state than the space surrounding it, a truer ground, a deeper valley, the wall of the bubble would begin to expand, and it would do so at a speed that current physics gives no obvious reason to expect would be anything less than the speed of light itself. There would be no warning that outpaces the event. No telescope trained on the right patch of sky would catch it approaching, because the wall of true vacuum would be moving at the exact velocity of the light that might otherwise have revealed it. It would simply arrive, everywhere within its reach, simultaneously and without ceremony, the old universe replaced by the new one instant by instant, the way a tide fills a hollow in sand, not gradually from one edge, but all at once as the water finally reaches it. It is worth pausing here, in the hush of wherever you are lying, to notice what is and is not being claimed. This is not a prophecy. It is not a countdown. The mathematics that permits this scenario is the same mathematics that, with only slightly different inputs, forbids it entirely, describes instead a universe settled comfortably and permanently into its lowest possible state, stable across durations so long that the word forever becomes, for all practical purposes, an honest description. The difference between these two futures, the stable and the metastable, does not hinge on anything mystical. It hinges on decimal places, on the fourth digit of a mass measured in gigaelectronvolts, on refinements so small that a decade of extraordinarily expensive, extraordinarily careful science has been required simply to move the needle from probable instability towards something closer to certainty, without yet arriving there. And even if instability is confirmed, even if every remaining measurement tightens the case rather than loosens it, there remains the matter of time itself, because the mathematics offers not a deadline but a probability distribution stretched across timescales so long that comparing them to the current age of the universe is like comparing a single grain of sand to the shoreline of a continent. The universe, as it stands now, is some 13.8 billion years old, a number that already strains the imagination, that already asks more of intuition than intuition can comfortably give. And yet the timescales physicists calculate for vacuum decay, in the scenarios where decay is possible at all, do not merely exceed this age. They exceed it by factors so large that the comparison itself begins to lose meaning, the way comparing a heartbeat to the lifespan of a mountain range loses meaning past a certain point, both technically true and somehow beside the point at the same time. The figure most often cited, when the calculation is run with the current best measurements of the Higgs and top quark masses, lands somewhere in the neighborhood of 10 to the power of 100 years or more before decay becomes likely on average across the observable universe. It is worth sitting with that number for a moment, not to grasp it. No one grasps it, not truly, not the physicists who calculate it and not the rest of us who only read about it before sleep, but to let its shape register, the way you might register the shape of a mountain range from a great distance without being able to count its peaks. A number that large does not describe a long time in any ordinary sense. It describes a kind of time that exists mostly as a mathematical object, a placeholder for an event so improbable that the universe will, by every reasonable expectation, exhaust its stars, its galaxies, its last flickers of radiation, and settle into a cold and featureless dark long before any bubble of true vacuum has a meaningful chance to form. This is, in its way, a kind of reassurance, though it arrives dressed in strange clothing. The instability, if it exists, is not a threat in any sense that maps onto human worry, human planning, human fear. It is not comparable to a diagnosis, or a storm on the horizon, or anything that unfolds on a timescale, a person, a civilization, or even a species could meaningfully brace against. It is closer to a property of the mathematics itself, a fact about the deep structure of the field that fills all of space. True, perhaps, in the same sense that a distant coastline is true, existing whether or not anyone ever sails far enough to see it. Knowing it does not change the light falling across the room right now. It does not change the quiet rhythm of your own breathing, slower now, perhaps, than it was at the start of this telling. And still, there is something the mind returns to, almost against its own will, in contemplating a fact like this. Not fear exactly, but a kind of vertigo, the sensation of standing at the edge of a scale so large that the ordinary handholds of thought no longer reach. Because the question was never really about a bubble expanding at the speed of light through the fabric of space. That is only the mechanism, the specific physical process by which an abstract mathematical possibility might, in some almost unfathomably distant future, become an event. The deeper question, the one that quietly threads beneath all of it, is about permanence, whether anything, including the very laws that govern matter and energy and time, is truly fixed, or whether even the deepest bedrock of reality is provisional, resting, as the valley in the Higgs potential seems to rest, not at the bottom of everything but somewhere partway down, held in place for now by a barrier that is real but not, strictly speaking, eternal. There is a peculiar comfort available here, if you are willing to receive it. Human lives, human civilizations, even the sun itself and the long, warm epoch of stellar light in which planets like this one can form and hold water and cradle something as improbable as thought, all of it will end, in the ordinary course of cosmic events, through mechanisms far more immediate and far better understood than vacuum decay. Stars exhaust their fuel. Galaxies drift apart as space itself expands. The available energy for complexity, for structure, for anything resembling life, thins gradually across tens of billions of years until even the slow, patient processes of decay and radiation have nothing left to consume. Vacuum instability, if it is real, sits so far beyond even that unimaginably distant horizon that it functions less as an ending and more as a kind of outer boundary condition, a statement about what is ultimately possible rather than a forecast of what is ultimately likely to be witnessed by anything at all. And perhaps that is the quiet gift hidden inside this entire strand of research. Not an answer to the question of how the universe ends, not yet, and perhaps not for many years still, but a widening of the frame in which the question can even be asked. Because to ask how a universe ends is also, unavoidably, to ask what it means for something to be stable in the first place, what it means to rest, to persist, to hold a shape across time without collapsing into something else. And it is here, strangely, that the physics of an unimaginably distant future begins to fold back toward something almost intimate, almost personal, something that has less to do with. And perhaps that is enough, not an answer, but a kind of company in the not knowing, a reminder that every generation before this one has lain down beneath some unresolved question, some vast dark ceiling of the unknown, and slept anyway, trusting the world to hold its shape until morning. The scientists working now, in laboratories humming quietly beneath the Franco-Swiss border, are only the latest in a long lineage of people who have looked up, or down, or inward, and tried to describe the edges of things too large to fully see. What separates their inquiry from those that came before is not the impulse, which is ancient, but the precision, the astonishing, hard-won precision of instruments that can register a particle's fleeting existence in units of energy so fine they would have seemed, to any earlier century, indistinguishable from magic. Consider, for a moment, the wider context in which this particular question sits, because the fate of the vacuum is only one thread in a much larger tapestry of endings that cosmology has begun, slowly and carefully, to sketch. There is the heat death, the most probable and most thoroughly understood of the universe's possible futures, in which expansion continues its long, gentle acceleration, driven by the dark energy that makes up most of the cosmos and whose nature remains, even now, essentially mysterious. Galaxies drift beyond one another's light. Star formation slows as the raw material for new stars is gradually exhausted, spent, dispersed. The universe does not so much end in this scenario as thin, spreading itself ever more sparsely across an ever-expanding volume, until what remains is less a cosmos than the memory of one, a cold and quiet dilution stretching toward a horizon with no far side. There is, too, the possibility of collapse, the mirror image of expansion, in which the outward push of dark energy might someday reverse, drawing everything back toward a single point in a mirrored echo of the very beginning, a big crunch answering the Big Bang across an almost unfathomable span of time. Current observations make this scenario seem unlikely. The acceleration of cosmic expansion appears, by every measurement gathered so far, to be increasing rather than slowing, but unlikely is not the same as impossible, and the honest posture of science has always been to hold multiple futures in mind at once, weighted by evidence, revised as evidence changes, never mistaking the current best guess for a final verdict. And then there is the vacuum decay this narration has spent so many quiet hours describing, different from both of these in a crucial way. It does not depend on the large-scale behavior of the cosmos, on how galaxies move or how fast space itself stretches. It depends instead on something far smaller and, in its way, far stranger, the local shape of a field that fills every point of space equally, indifferent to galaxies and stars and the distances between them, a property of the vacuum itself rather than a property of what the vacuum contains. It could happen, in principle, in the emptiest reach of intergalactic space or in the room where you are lying right now, because the field does not distinguish between the two. It is, in this sense, the most democratic of cosmic endings, and also the strangest, because it does not creep. It does not build. It does not announce itself in advance through some gradual dimming or gathering chill. It would simply begin, somewhere, sometime, and then arrive. But held against the almost incomprehensible timescales already described, this strangeness softens into something closer to abstraction, a thought experiment more than a genuine subject of concern. The heat death, slow and vast as it is, likely still occurs on a timescale many orders of magnitude shorter than the timescale for vacuum decay, meaning that even in the scenario where our particular corner of spacetime is not perfectly stable, it will very probably outlast every star, every galaxy, every trace of light in the observable universe long before that instability has any meaningful chance to resolve. In other words, whichever ending comes first, it will almost certainly not be this one. Vacuum decay, if it is real, is less an ending in its own right than an outer boundary marking the furthest edge of possibility, the point past which even nothing has stopped being able to change. There is something worth sitting with in that thought, turning it over slowly the way you might turn a smooth stone in your palm before sleep. That even nothingness, in the strict physical sense, is not truly static. That the vacuum of space, so often imagined as an absence, a blankness, a mere backdrop against which the real business of existence unfolds, is in fact a thing with structure, with depth, with a shape that can be measured, mapped, and, perhaps, someday, however many careers and collaborations from now, finally understood well enough to say, with something approaching confidence, which of these vast slow endings, if any, the universe is quietly moving toward. Consider, for a moment, the number itself, the one that started all of this. 125.25 billion electron volts. A mass. A weight, in the strange currency of particle physics, belonging to a boson that exists for less than a septillionth of a second before dissolving back into the particles that made it. It sounds impossibly small, a fact suited only to the inside of a laboratory, and yet this single number, pinned down through years of collisions inside a 17-mile ring beneath the French and Swiss countryside, turns out to be one of the threads holding the fate of everything in place. Move it slightly, nudge it up, nudge it down, adjust it by a fraction so small most instruments of the last century could never have caught it, and the calculation changes. The valley the universe is sitting in becomes deeper, or shallower, or simply different. This is the quiet, almost unbearable intimacy of the thing. That the long-term fate of all matter, all light, all the slow turning of galaxies, should hinge on a measurement made by machines built by hands, read by minds, argued over in conference rooms with bad coffee and fluorescent lighting. The universe does not confide its secrets easily. But here, perhaps, it has left one in plain sight, encoded in the mass of a single particle, waiting for someone patient enough to weigh it correctly. And weighing it correctly has taken decades. You have to understand how delicate this is. How many other numbers depend on getting this one right? The mass of the top quark, heaviest of all known fundamental particles, factors into the same equation, tangled together with the Higgs mass in a relationship so sensitive that a difference of a single GeV, a rounding error by the standards of everyday physics, can tip the entire vacuum from merely metastable into something closer to stable, or push it further toward outright instability. For years, physicists have circled this ambiguity, refining detectors, refining collision energies, refining the statistical machinery used to separate true signal from the vast noise of proton collisions happening 40 million times each second. Each refinement narrows the range. Each narrowing brings the number into slightly sharper focus. And what that focus reveals, again and again, is the same unsettling picture. Not certainty of collapse, not proof of safety, but a vacuum poised precisely at the edge, close enough to instability that the universe seems, in some sense, to be balancing on a knife's edge that is impossibly thin and yet has held, without complaint, for nearly 14 billion years. There is a strange comfort hidden inside that impossibly long endurance, if you let yourself feel it. Whatever this knife's edge is, however narrow, however fine, it has not yet given way. Not during the violence of the early universe, when temperatures and energies dwarfed anything a human-built collider could ever hope to reach. Not during the long, slow cooling that followed, as space expanded and matter condensed into the first stars, the first galaxies, the first patient rhythms of light and shadow. Not during any of the countless high-energy events that have rippled across the cosmos since, the collisions of neutron stars, the violent deaths of massive suns, the impossible pressures inside black hole formation. If the vacuum were truly fragile, if the barrier separating our false calm from a lower, truer calm were as thin as some models suggest, one might expect the universe to have found its way through by now, tripped by cosmic ray collisions carrying energies that no earthly accelerator will ever match. And yet here we remain. Here you remain, lying still, listening, thinking, existing in a pocket of space that has not yet decided to become something else. Some physicists take this endurance as its own kind of evidence, an argument not from calculation but from survival, the simple observation that 14 billion years of unbroken existence places a lower bound on how unstable this vacuum could possibly be. Others are more cautious, pointing out that survival tells you only that decay has not happened here, not that it could not happen, not that somewhere unfathomably distant, beyond the reach of any light that will ever touch us, it might already be underway, spreading outward at the speed of light itself, erasing everything it touches with such perfect efficiency that no signal, no warning, no flicker of change could ever precede it. This is the particular cruelty of vacuum decay as a hypothesis, that even if it were happening, right now, somewhere unimaginably far off in the folds of space, you would have no way of knowing. The bubble wall moves at light speed. Its approach and its arrival are, for any observer inside its path, the same instant. There is no eve of destruction. There is only the world as it has always been, and then, without transition, without warning, a different world entirely. Assuming there is a version of you left to notice the difference, which, in most models, there quietly is not. There is, strangely, something almost merciful hidden inside that cruelty, if you turn it just slightly in the light. No dread, no countdown, no slow unraveling to witness, no grief to carry through a final century or a final hour. Only the world, exactly as it has always been, up until the instant it is not. And in that instant, no pain, no fear, no awareness of loss, because the very particles capable of carrying awareness are, in that same fraction of a moment, being rewritten into something else entirely. It is, in its way, the gentlest catastrophe physics has ever proposed. a death with no experience of dying. A door with no threshold, no corridor leading up to it, no hand on the knob, simply one room, and then, without seam, another. Perhaps this is why the idea unsettles less than it should, once you sit with it long enough. It asks nothing of you. It offers no warning to dread, no slow erosion to mourn, no final flicker of a dying star to watch from a darkened porch. It simply exists, out at the furthest edge of possibility, a shape drawn in the mathematics of quantum fields, patient and indifferent, asking only to be correctly measured. And measurement, as it turns out, is the quiet, unglamorous heart of everything cosmologists have learned about how this universe might end. Not prophecy, not omen. Numbers, refined generation after generation, each one a little closer to true, each one narrowing the field of what remains possible. But vacuum decay, for all its strange and sudden violence, is only one candidate among several, and perhaps not even the most likely. There is another ending, far older in the history of physics, far gentler in its unfolding, that many cosmologists still consider the most probable fate of all. Not a bubble wall racing outward at the speed of light, but something closer to a long exhale. A cooling, a stretching, a universe that does not tear or collapse or rewrite itself in an instant, but simply, slowly, runs out of difference. Physicists call it heat death, though the name is somewhat misleading, conjuring images of fire and burning when the truth is closer to the opposite. An ending defined not by heat but by its absence, by the slow erasure of all the differences that make heat, and motion, and change, and life, possible in the first place. To understand it, you have to think not about explosions or collapses, but about a quantity most people never think about at all. Entropy, the measure of disorder, of how spread out and undifferentiated energy has become. In the earliest universe, entropy was low. Matter and energy existed in tight, ordered pockets. Hot stars separated from cold space, concentrated matter separated from emptiness, difference upon difference upon difference, and it is precisely in those differences that all possibility lives. Heat flows from hot to cold. Rivers flow from high ground to low. Stars burn because their cores are far hotter than the vacuum surrounding them, and that gradient, that difference, is the engine driving every process worth naming, every reaction, every heartbeat, every thought passing through a mind. Take away the differences, and you take away the engine. Nothing remains to drive change forward. Not because matter and energy have vanished, but because they have spread so evenly, so completely, across the vastness of space that no gradient remains steep enough to power anything at all. Picture it slowly, the way sleep might picture it. Not a shattering but a settling, over spans of time so long that today's 14 billion years would register as barely a heartbeat by comparison. The stars, one by one, exhaust their fuel and go dark, their light fading not in violence but in exhaustion, the way a candle gutters when the wax finally runs low. New stars form more rarely as the raw material for star birth. The great cold clouds of hydrogen drifting between galaxies grows thinner, spent, unreplenished. Galaxies themselves drift further apart as the expansion of space carries them beyond each other's reach, so that eventually, unfathomably far in the future, any observer remaining would look out at a sky containing nothing at all beyond their own galactic remnant. No other galaxies to see, their light having outrun the very possibility of ever arriving, swept away by an expansion that only accelerates with time. Black holes, for a while, become the last significant structures left, swallowing what remains of ordinary matter, growing vast and patient in the emptying dark. And then, over spans of time that make even galactic ages look brief, even black holes begin to fade, releasing their mass slowly back into the universe as a faint mist of radiation, a process so gradual it makes the burning of a star look instantaneous by comparison. What remains, at the very end of this long unwinding, is a universe stretched thin beyond imagining, a scattering of particles so distant from one another that they might never again interact, adrift in a darkness with no temperature gradient left to exploit, no structure left to build, No difference left anywhere to make any further change possible. This is the state physicists sometimes call maximum entropy. Not chaos in the way the word is often used, not disorder in the sense of wreckage or ruin, but something closer to perfect, featureless evenness. A bath drawn to exactly the same temperature throughout, with no warm current left to stir it, no cold edge left to feel. A universe, if you could still call it that, at rest in the deepest sense the word allows. No clocks would tick, because a clock requires change to measure, and change requires difference, and difference is precisely what has run out. Time itself, in any meaningful sense, would cease to mark anything at all, not because time has ended, but because nothing remains to happen within it. There is a peculiar stillness in imagining this, one worth letting settle rather than rushing past. Because heat death, unlike vacuum decay, offers no single moment of transition, no wall racing outward at light speed, no instant when everything changes into something else. It is not an event. It is the slow withdrawal of events themselves, one by one, until none remain. A universe winding down not with a crash, but with a fading. The way a struck bell's ring grows quieter and quieter until the ear can no longer distinguish it from silence, though the air, technically, is still moving, still vibrating, still carrying the faintest trace of a sound too faint to call sound anymore. Astronomers place this ending almost unfathomably far in the future, not millions of years, not billions, but numbers so large they exceed ordinary description, timescales measured in googolls, a 1 followed by 100 zeros, dwarfing the current age of the universe so completely that all of cosmic history so far, every star that has ever burned, every galaxy that has ever turned, the entire 14 billion year span containing every thought any living creature has ever had, would amount to less than the first flicker of an eye blink in a night stretching on forever. And yet even within that unimaginable expanse, there are strange, quiet possibilities tucked into the mathematics, moments that occasional physicists have wondered about late in careers otherwise devoted to more solid ground. In a universe so vast, so old, so thoroughly randomized, could enough particles happen, by pure chance, to briefly reassemble into something ordered again? Not through any process, not through gravity or stars or life as it has ever been understood, but simply through the blind churn of probability, given enough time, and heat death offers more time than any mind can properly hold. A fluctuation, a brief, spontaneous dip back toward order, vanishing again almost as soon as it forms, a ripple on a pond so still it has forgotten it was ever capable of rippling at all. Physicists call these hypothetical structures Boltzmann brains, after the 19th century physicist whose work on statistical mechanics first made such strange calculations possible, and the concept exists less as a serious prediction than as a kind of cautionary tale within cosmology itself, a thought experiment revealing just how strange the deep mathematics of entropy can become when pushed to its furthest, most patient extremes. Most physicists regard it as a paradox to be resolved rather than a fate to be expected, a sign that some assumption in the models still needs refining rather than a genuine glimpse of things to come. But its mere possibility, however remote, however contested, says something worth holding on to, that even in the flattest, quietest, most exhausted version of the universe imaginable, absolute nothing may still, on the longest of timescales, remain slightly out of reach. Whether this is the ending our universe is actually moving toward, heat death, this long unwinding into featureless calm, depends on a handful of measurements that remain, even now, frustratingly incomplete. It depends most of all on the nature of dark energy, that strange pressure discovered only in the final years of the 20th century, the invisible force accelerating the expansion of space itself, pushing galaxies apart faster with every passing epoch. If dark energy remains exactly what current observations suggest, a cosmological constant, steady and unchanging across all of cosmic time, then heat death is not merely one possibility among many but the single most probable ending physics currently has to offer, the quiet default the universe settles into once every flashier alternative has been ruled out. But dark energy's constancy is itself an assumption still being tested, still being measured, still capable of surprising the instruments built to study it. Recent surveys, mapping the positions of millions of galaxies across billions of years of cosmic history, have begun probing this constancy more precisely than ever before, watching for the faintest hint that the force driving cosmic expansion might not be constant at all, but slowly, imperceptibly, evolving, weakening, perhaps, with the turning of cosmic time, the way a note struck on some vast instrument might fade not to silence but to a different pitch entirely. This is not settled science. It would be dishonest, and worse, unkind to the spirit of patient inquiry that has carried this story so far, to present it as anything more than what it is, an intriguing hint, a statistical whisper at the edges of enormous datasets, the kind of signal that excites physicists precisely because it might be nothing, a trick of sampling or systematic error, and might also, if it holds beneath years of further scrutiny, quietly rewrite everything assumed about how this universe is going to end. Instruments mapping the large-scale structure of the cosmos, vast surveys tracking the positions of galaxies and the faint imprint of sound waves frozen into the distribution of matter since the universe's infancy, have begun to suggest, tentatively, that the pressure driving cosmic acceleration may not be the fixed, eternal constant it was long assumed to be. If that suggestion holds, if dark energy is genuinely evolving rather than static, then the long, slow slide toward heat death is no longer the guaranteed default. Other endings, once considered closed possibilities, quietly reopen. Consider, for a moment, what it would mean if dark energy were not merely weakening but reversing, if the force presently tearing galaxies apart from one another were to slow, halt, and eventually turn inward, becoming something closer to gravity's old and familiar pull. Cosmologists have a name for this ending too, older even than heat death as a concept, dating back to the earliest days of relativistic cosmology, when Einstein's equations first revealed that a universe full of matter, left to itself, wants to collapse under its own weight. They call it the Big Crunch, and though it fell out of scientific favor once dark energy was first discovered accelerating the expansion rather than resisting it, it has never entirely vanished from the range of things physics considers possible, waiting patiently at the margins of the models for the data to shift, however slightly, back toward it. Picture it slowly, the way you might picture the heat death that came before, letting each stage settle before moving to the next. If the expansion of space began to reverse, not now, not soon, but at some point unfathomably distant, should the underlying physics permit it, the vast emptiness between galaxies would begin, ever so gradually, to close. Distances that once seemed to grow forever would instead start shrinking, first so slowly as to be undetectable across a human lifetime, then a little faster, then faster still, the way a stone dropped from a great height gathers speed not suddenly but continuously, each moment adding to what came before. Galaxies now separated by hundreds of millions of light-years would begin, over spans of time longer than the universe has yet existed, to draw nearer to one another. The night sky, so dark and sparse in the heat-death scenario, would instead grow steadily brighter, more crowded, more luminous, as galaxies once invisible across the gulf of cosmic distance came close enough to be seen, and then closer still, until the sky itself became a wall of light. And it would not stop there. As collapse accelerated, the cosmic microwave background, that faint, ancient afterglow of the universe's birth, cooled now to barely 3 degrees above absolute zero, would begin, for the first time since the earliest moments of cosmic history, to warm. Slowly at first, imperceptibly, and then with mounting speed, the temperature of the universe as a whole would climb, reversing 14 billion years of patient cooling in a compressed final act, stars and galaxies and the great structures of the cosmic web crushed together with increasing violence, their individual identities dissolving back into the kind of undifferentiated, blazing density that once, long ago, existed only in the universe's first fractions of a second. Where heat death ends in a whisper, the Big Crunch would end in something closer to a scream, not literally, for there would be no ears left to hear it, No minds left to register the violence of a universe folding back in on itself, matter and energy and space compressed past every threshold that once separated one particle from another, collapsing not into nothing but into something almost impossible to describe, a density and a temperature approaching, perhaps, the same singular conditions, from which everything is believed to have first emerged, all those billions of years ago, in the earliest instant physics can meaningfully describe. Whether that final collapse would simply end, snuffing out space and time together in a point with no further meaning, or whether it might instead become a kind of threshold, a crushing so complete that it triggers, somehow, another beginning, another expansion, another universe unfolding outward from the ashes of this one in a cycle that repeats without evident end, remains one of the oldest and strangest questions cosmology has never quite managed to close, a question that some physicists have taken seriously enough to build entire models around, called cyclic cosmology, in which the universe does not simply end but breathes, expanding, collapsing, and expanding again, an oscillation stretching across cycles so vast that our current age, our 14 billion years of stars and light and quiet human wondering, might be only one exhale in a rhythm with no first breath and no last. It is a beautiful idea, in its way, and beauty alone has never been proof of anything, a lesson physics has learned and relearned across centuries of elegant theories that turned out, when measured carefully enough, to simply be wrong. Most current observations, in fact, point away from a crunch entirely. Dark energy, as best current instruments can tell, seems to be pushing outward rather than weakening towards some eventual reversal, which is precisely why heat death remains the leading candidate rather than a beautiful alternative that the evidence, so far, declines to support. But declines to support is not the same as rules out. And so the big crunch waits, patiently, at the edge of what remains possible, the way vacuum decay waits, the way every other ending waits, held in a kind of suspended candidacy by data that is good, remarkably good, but not yet good enough to close every remaining door. This, in the end, is the honest shape of the story. Not a single answer arriving neatly at the end of a long investigation, but a set of possibilities, each grounded in real mathematics, real measurements, real instruments built by real hands over real decades, each waiting on the next refinement, the next survey, the next careful weighing of some quantity too subtle for the last generation of telescopes to catch. Heat death, patient and probable, a universe cooling into featureless stillness across timescales too vast for numbers to feel real. Vacuum decay, sudden and silent, a bubble wall racing outward at light speed, rewriting the very laws that hold matter together, arriving before any warning could ever precede it. The big crunch, ancient and strange, a long collapse back toward the density of beginnings, perhaps ending entirely, perhaps beginning again. Three shapes for an ending that has not yet happened, drawn from the same universe, the same equations, the same patient work of measurement that found the Higgs boson 13 years ago and has been refining its mass, its implications, its whispered warnings about the shape of empty space, in every year since. And perhaps what matters most, lying here in the dark with all of this turning slowly through your mind, is not which of these endings turns out to be correct. Perhaps what matters is the strange, quiet privilege of being a part of the universe capable of asking the question at all. Every atom in your body was forged inside a star that lived and died long before the sun existed, scattered across space by violence, gathered again by gravity, shaped by chance and time into something that can lie still in the dark and wonder about its own eventual unmaking. That is not a small thing. That is, if anything, the entire strange miracle folded inside all of this, that matter, arranged just so, becomes capable of turning around and studying the very forces that arranged it, of building machines 17 miles in circumference to weigh a particle that exists for less than a trillionth of a second, of mapping the positions of millions of galaxies across billions of years of light just to ask whether the force pushing them apart is constant or changing, of doing all of this not because survival requires it, but because curiosity does. The universe does not owe us these answers. It offers no guarantee that a species built from stardust, occupying a single small planet around an unremarkable star in an ordinary spiral galaxy, should ever be capable of understanding its own eventual fate, let alone measuring the particles and forces responsible for deciding it. And yet, slowly, patiently, across generations of careful work, that is precisely what has begun to happen. Not a final answer, not yet, and perhaps not for a very long time still to come, but a narrowing, a sharpening, a vacuum measured a little more precisely with each passing year. A dark energy watched a little more closely with each new survey. A universe that remains, for now, exactly as uncertain and exactly as beautiful as it has always been, holding its breath somewhere between a whisper and a scream, waiting to see which ending, if any, it has been moving toward all along. For tonight, that uncertainty is enough. Let it settle over you the way the dark settles over a quiet room, not as something to solve, but as something to rest inside, vast and unhurried, indifferent to any particular certainty, in a universe that continues, for now, to hold together, one patient measurement at a time, all the way into sleep.